After the fantastic keynote by Joel, we are continuing on the theme of reinforcement learning. My name is Katja Hoffmann. I work at Microsoft Research in Cambridge, and I'm very pleased to be your session chair for today. We will start the session with 4 spotlights. After that, there will be 1 oral presentation, and we will conclude with another 5 spotlights. So the first talk will be given by Bo Wagner, and he will be talking about, is this yours? A smooth analysis of the greedy algorithms for linear contextual bandits.
No, this is not on, right? Is this working? Oh, there we go. Welcome to the session. Yes, so yes, I'll be talking about smooth analysis of greedy for linear contextual bandits. This is with Sampath, Jamie, Aaron, and Stephen. Is this better? Is this better? Okay. Good. So linear contextual bandits is a model for repeated decision making many of us are familiar with. So each day a set of options arrive, and we observe some contextual information about each option. You can think of these as vectors in R to the D. Each option, our model of the world is that there's some linear function that maps its context to an expected reward if we were to choose that function. And initially we don't know these functions, so we need to learn them in order to make good decisions. Okay, and we'll be doing this repeatedly over time. We choose some choice. We observe not the exact expected reward, but some noisy version of it centered around that expectation. And we can use this data to learn about that linear function, and then we repeat. Okay, so this paper is about studying the greedy algorithm for this problem. So there you just take the data you have so far, estimate each linear function, and then choose the option at the current time that maximizes your expected reward, not thinking about exploring or the future or anything. And of course, we know in the worst case, this can have arbitrarily bad performance because some adversary could select the context in a way to mess this algorithm up. So the conventional wisdom is to say that there's an exploration-exploitation trade-off for these bandits problems. In particular, for this problem, exploration seems necessary, but this paper is going to question that by introducing a small assumption. So we're going to do what's often called smooth analysis. We're going to assume that there's a bit of randomness in the world. So our context can't be completely chosen adversarially. Maybe an adversary chooses some means mu, but then there are some perturbations to these contexts. Let's just say normal with some very small variance. Okay, and then the true contexts that arrive are these perturbed versions. Okay, and then the question is this randomness going to be enough to allow actually this greedy myopic algorithm to perform well? Okay, and the answer is going to be yes. So our main result is that with a small amount of initial training data to jumpstart the algorithm, greedy can actually achieve good performance for this problem just due to these small perturbations in the context. Okay, and this builds on some results and ideas of this prior paper of Bastani et al. Okay, and we can make this a bit more quantitative. So the amount of training data depends on the size of the perturbations and also on these linear functions on the smallest norm. And the regret, the performance of the algorithm is measured with regret, and it looks like square root t, where t is the number of time steps. So with this perturbation assumption, we're achieving a similar regret to what you would expect with a sophisticated explore-exploit algorithm. So in this setting, we can say that exploration seems to not be fundamentally necessary with this assumption. Oh, sorry, let me first mention, so we have some lower bounds that say that this dependence of the training data on these parameters is necessary. But in a similar setting, which is called the single parameter setting, where all of these linear functions are the same map, but only the contexts differ, actually you don't need any initial training data at all. So there's really no exploration at all necessary to solve this problem. Okay, so let me wrap up with some motivation for why you'd study this problem beyond the fact that it's interesting. So first is just understanding when is exploration necessary, which seems like an interesting and fundamental question for these bandits' decision-making problems. And the second is to understand myopic or short-sighted decision-making in contexts where you think that's going to happen or important. So there may be incentive reasons, so the person making the decision today is different from the person making the decision tomorrow, and they're just caring about their own utility. And you can also think of fairness or ethical reasons. So if you're doing medical treatments, it may be unfair to use the current patient to explore just in order to learn for future patients. Okay, so, and there's lots of future directions to explore these kinds of questions. Thank you.
Thank you. The next talk will be by Han Shao, and she will be speaking about almost optimal algorithms for linear stochastic bandits with heavy-tailed payoffs.
Hello, everyone. Today, I'm here to introduce our paper, Almost Optimal Algorithm for Linear Stochastic Bandits with Heavy-Tailed Payoffs. I'm Han Shao, and we come from the Chinese University of Hong Kong. Linear stochastic bandits have been applied into online advertising, online recommendations, and a lot of other applications. And in linear stochastic bandits, you are given a set of arms represented by d-dimensional vectors, and at each time t, you have to select an arm xt, and then observe a stochastic payoff, which is a linear function of xt plus a stochastic noise. The goal is to maximize the cumulative payoffs. And previously, it is quite common and popular to assume that the noise follows a sub-Gaussian distribution, which means that the variance of the noise is bounded and there are very few extreme values. But in the real world, there are a lot of heavy-tailed cases with possibly infinite variance, and which means that there are more extreme values. Take high-probability extreme returns in financial markets as an example. Here, we draw the Nasdaq returns in the past 50 years, and we could find that its tail is heavier than a Gaussian distribution. And there are a lot of other heavy-tailed cases, like delays in communication networks, biological data, and etc. So we try to generalize the previous sub-Gaussian assumption to a heavy-tailed one. And classical Martian bandits with heavy-tailed payoff has been started by Bubeck, etc. in 2013, where they assume that the 1 plus epsilon moment of the noise is bounded for epsilon in 0 to 1. So in our work, we adopt the same assumption on noise. Actually, this is indeed a weaker assumption because the second moment of a sub-Gaussian random variable is always bounded. And our problem has been started by Medina and Yang in 2016. Here you could see the summary of the previous work, and you could find that the Medina and Yang's work, they only achieve the regret of t to the power of 3 over 4 when epsilon equals 1, which seems loose because the previous work for Martian bandits with heavy-tails could achieve square root t. So the most interesting problem we are considering is whether we can achieve square root t. We propose 2 algorithms and answer this question affirmatively. So one of our algorithms is called Menu, and this algorithm is based on the technique of median of means, which is a common technique to deal with heavy-tails. And both Medina and Yang's work and our work adopt this technique, but the difference is that we divide all history payoffs into k groups and calculate the least square estimates for each group, and then take the median of means over all these estimates. But for their algorithm MOM, they take median of means of payoffs of specific arm, and so it has to pull each arm a lot of a number of times, which is very costly, and then they calculate the least square estimate with all these processed payoffs. Our menu outperforms the MOM both theoretically and empirically. And besides the menu, we also propose another algorithm named the tofu, and here you can see the results of regret bounds in this paper. We derive the lower bounds of this problem, and you can see that both of our algorithms achieve the optimal rate up to logarithmic factors. And when epsilon equals 1, our algorithm achieves the square root t. So although we have derived some better results, but there are still a lot of open problems in linear stochastic bandits with heavy tail payoffs. So if you are interested in more details, you could come to our poster. Well, the room number should be 517. Here is a mistake. And our poster number is 158. Yeah, thank you.
The next talk will be by Philippe Belbit-Paris, and he will be speaking about end-to-end differentiable physics for learning and control.
Hi, I'm Philip. I'm going to be talking about end-to-end differentiable physics for learning and control. This is joint work with Kevin Smith, Kelsey Allen, Joshua Tenenbaum, and Zico Coulter. The deep learning models used nowadays are usually composed by a sequence of modules that are stacked together to form a larger system. And everybody knows by now that these models are very good at learning complex relations. But the flip side to that is that learning these complex relations requires a lot of data. Now, the physics that governs the motion of bodies can get pretty complex. So one might think, okay, let's just take a bunch of data and learn that. But why would we want to learn that? After all, the dynamics equations that govern the motions of bodies, they're already known. This problem has been solved, basically. So our motivation here was to try and take this structured physics knowledge and embed it into these large end-to-end systems so that we don't have to relearn these things that we already know at the cost of a lot of data. But of course, that for this to work, we need our physics simulations to be differentiable, and this is what we set out to do in this work. Others had done this type of work in the past, and their methods were usually either to run a complete physics engine using automatic differentiation tools, or use numerical gradients, or even to just try and learn the dynamics from data using differentiable models. Our approach, however, was to try and formulate a physics engine that would provide the gradients we need in an analytical form. So here's a quick overview of how we do that. We first need to formulate our rigid body dynamics. And so to do that, we start with the Newtonian dynamics equations. And then we add on that the constraints that define rigid body dynamics. Those are the equality constraints that define stuff like joints, contact constraints that make sure that bodies don't interpenetrate, and friction constraints that define frictional forces. The contact and friction constraints have what are called complementarity conditions attached to them, so that we end up with rigid body dynamics formulated as a linear complementarity problem, or LCP. All this is nothing new. This is a standard way of modeling rigid body dynamics. But what we do on top of that is that we then write down the optimality conditions for this LCP, and then take the matrix differentials of that. And what we end up with is a system of linear equations where we can solve to find the differentials that we want. But what's really important here is that since we have already factorized the LCP matrix and solved it in the forwards pass when running the simulation, to get the gradients we want in the backwards pass, we just need an additional solve. And what this means is that we can get a fast backpropagation because we can effectively differentiate through our simulation without adding any computational complexity to just running the simulation. Now here's some of the things we can do with this type of system. In this task, we try to learn the mass of a chain by observing it collide with a ball of known mass. So we observe these objects collide, we observe the position of them after the collision, and then we take an estimate of the mass of the chain and do a simulation, and then we do gradient descent to try and minimize the difference between the simulated positions and the actually observed ones. And we're able to recover the mass of the chain in a few steps. We also run a variation of this experiment in which we vary the length of the chain to compare our analytical gradient with numerical gradients using finite differences. And what we see is that as you increase the number of links in the chain, and thus the number of physical parameters in our simulation, the cost of running the numerical gradients increases much faster. In this other task, we predict the evolution of simulated billiard balls from visual images. So what we do is we take a sequence of frames where these balls are bouncing around, we pass it through a convolutional neural network to get the position and velocity of the objects, we step it forwards in time using our physics engine, and then we use another network to generate a predicted image. And what we see is that we can efficiently learn to predict these types of dynamics. And since our engine is differentiable, we can train this model end to end. Finally, we use our physics engine for model-based control in the Atari Breakout game. What we do here is we take the input frames from the game, we segment it into physical objects, and this is not learned, we do this hard code, but then what we do on top of that is we learn the parameters that govern the motion of the paddle and the ball, and then we use this differentiable dynamics model with IOQR for control, and we're able in as little as 1,000 steps to achieve a reward that's almost as high as a double QN benchmark, which uses over 10 million steps to just get a reward that's starting to get a little above zero. If you want to learn more about this work, our poster is number 38 this morning. Our code is available online. Thank you for listening.
The next talk will be by Ronan Fruit. and he will be speaking about near-optimal exploration exploitation in non-communicating Markov decision processes.
Okay, thanks. Hi, everyone. I'm Ronan. And this talk is about how to achieve a near-optimal exploration-exploitation trade-off in non-communicating MDPs. So I agree that this title may seem a little bit abstract, but to put it slightly more simply, what I will talk about is the exploration-exploitation dilemma in RL when the state space is misspecified. Okay, what does it mean? Let me start with an example that is now quite famous in RL, the breakout game. So no matter which algorithm you want to apply to solve this task, you need to specify the state space to your algorithm. So either explicitly or implicitly in the architecture, but it's necessary in order to be able to learn. Now, in these examples, perhaps the most intuitive state space that we could define if we only assume a very limited knowledge about the game is the set of all plausible configurations of the wall, the ball, and the paddle, which are the three key components of the game. Now, let's consider three states belonging to this space. The first state on the left, S1, is just the initial state of the game. Now, the state in the middle is a plausible state that you might observe after playing the game for some time. And finally, the state on the right is still valid with our definition of state space, but as you can see, because there is a hole in the brick wall, it's clearly not reachable from S1, and so it will never be observed. Now, here comes my definition of a misspecified state space, when there exists at least one state that is not observable from the initial state, but at the same time, it's very difficult to explicitly exclude these states from the definition of the state space without a strong prior knowledge on the environment and its dynamics. Okay, so now you might ask me, okay, why do we care? I mean, these states are not reachable in any case, right? Well, my answer to this question is that all existing methods that are known to efficiently balance exploration, exploitation in RL, and that in addition comes with theoretical guarantees, either on the sample complexity or the regret, they all rely on the same optimism in the face of uncertainty principle. But they also all fail to learn when the state space is misspecified. And to illustrate how bad these algorithms can perform in this case, let's consider a very simple RL example with a single state S and two actions A0 and A1. Now, this is basically a stochastic multi-unbounded problem, and an optimistic algorithm such as UCB is known to be the optimal strategy to drive exploration in that case. Now, what if the state space is misspecified? So there is an additional state S prime not reachable from S. Well, let's look at what happens if we apply the same kind of techniques. So by optimism, all the actions that are never been visited should be assigned an optimistic reward equal to the maximal reward, so 1 in that case. Now, of course, this is the case for all the actions in S prime because S prime is never visited by definition. Now, because of the optimistic reward, the algorithm is very tempted to try to move to S prime. Okay, but at the beginning of the learning procedure, it's equally plausible from the point of view of the algorithm that A0 or A1 move to S prime. So let's say that the algorithm starts by playing A0. Well, after playing A0 for some time and never observing a transition to S prime, because of course this transition does not exist, the algorithm will start figuring out that probably A1 is more likely to move to S prime, or at least with higher probability. So it will try to play as A1. Now the same thing will happen, so the transition to S prime will never be observed, and so the algorithm will start playing A0 again, and so on and so forth. So basically, the algorithm is stuck in an infinite loop trying to play A0 half of the time and A1 the other half. Okay, and now you might wonder, but what if you just remove S prime from the definition of the state space? Well, my objection to this is, in that case, your algorithm, if S prime is actually reachable from S, your algorithm might be stuck playing a suboptimal action in S, but it should try to move to S prime to get the high rewards. Okay, so another way to see why these kind of techniques fail is to look, perhaps more theoretically, to the regret bounds of these algorithms. So they all have a regret that scales linearly with the diameter and total number of states of the MDP. But it turns out that a misspecified state space is equivalent to an infinite diameter. So the bound becomes vacuous. What we did in this work is to design an algorithm that is able to adapt to the part of the MDP restricted to the states that are reachable from the initial state. And the regret scales linearly with the diameter and number of states of this restricted MDP. So this is great. Now I'm sure that you are all excited to know how we solve this problem. So please come to our poster. Thank you.
The next talk in this session will be an oral presentation. So this is a 15-minute slot. And I would like to remind you that at the end of this presentation, you will have the chance to ask questions. So if you do have questions, prepare to stand up and go to the microphones.
Hello, everyone. I'm Jung Trok from UIUC. This is a joint talk with Alexander Protier and Damian Ostranos at KTH. A real-world reinforcement learning wants to control systems with very large or even infinitely large state and action spaces. However, for such large systems, classical RL algorithms exhibit low performance in practice and also have poor theoretical guarantees since their regret or sample complexity grows with the number of states S and the number of actions A. This contrasts with the recent success of RL algorithms, such as deep Q networks, which are able to quickly learn optimal policies even in very large systems. One reason for this success may stem from the fact these algorithms implicitly exploit an underlying structure of the dynamical systems. For example, the fact that taking similar action at similar states may produce similar outcomes. In this work, we aim at providing theoretical tools to understand structural RL problems. More specifically, we wish to design RL algorithms that optimally exploit a known structure. To do so, we formally formulate regret minimization problem with structure, and an overview of our results are as follows. In the first theorem, using some solution of a semi-infinite linear programming, we identify the regret fundamental limits of any learning algorithms with any structure. And in the second result, we quantify these limits in the case of ellipsis structure, and we show that exploiting the structure can drastically reduce the regret to a value that does not scale with the number of states or number of actions. And finally, inspired by the semi-infinite LP in the first theorem, we propose an algorithm that optimally exploits structure and achieves the minimal regret. And here is our model. We consider Markov decision process with finite states and action spaces. And on MDP phi is defined by P and Q, specifying transition probabilities and reward distributions. And we define a structure denoted by capital phi as the set of all possible MDPs that verifies some properties known in advance. And if we have no prior knowledge, the structure capital phi is just the set of all the unstructured MDPs with any transition probability and rewards. So as a common example of structure, we can consider ellipsis structure where state and action pair are embedded in D times D prime dimensional spaces with some metric. And the transition probabilities and average reward are ellipsis continuous with respect to the metric with some ellipsis constants L and L prime. Intuitively, this ellipsis continuity means that taking similar action at similar states produces similar state transitions and rewards, where the similarity becomes stronger as the ellipsis constants L and L prime become smaller. Then for a given structure, any arbitrary given structure, our goal is to design an algorithm that optimally exploits the structure and achieve the minimal regret for any MDP satisfying the structure. So here, as usual, the regret is defined as the difference between the maximal accumulated reward one can obtain when knowing the true MDP versus total reward accumulated by an algorithm that knows only the structure and so needs to learn the true MDP. So for this regret minimization problem with structure, we first provide a problem-specific regret lower bounds of any algorithm for any given MDP phi from any arbitrary structure. And we show that the regret of any algorithm cannot be less than k of phi times log of time t, where k of phi is the optimal value of the semi-infinite linear programming with variable eta. Here, eta of xa represents the exploration rate of states and action pair xa, defined as the number of visiting set xa divided by log t. And delta of xa is the instantaneous regret by taking action A at state X instead of an optimal action. This LP finds exploration rates that minimize the regret and verify a set of constraints defined by the feasible set F of phi. Each constraint inequality in F of phi corresponds to a necessary condition on exploration rates to distinguish the given MDP phi from a confusing MDP psi. Here, psi is also verify the structure, but has different optimal policy than the given MDP phi. Hence, the feasibility of eta in the constraint is a necessary condition in order to statistically ensure the estimation of optimal policies. And a solution eta star from the LP corresponds to an optimal exploration that is feasible and has minimal regret. Note that in general, the number of constraints in the feasible set F can be infinitely many, and thus it is extremely challenging to analyze or solve this semi-infinite LP. But for ellipsis structure, we managed to simplify the feasible set, and we were able to quantify the potential gains from exploiting the ellipsis structure as follows. In the simplified feasible set F-lib, when constraining necessary exploration on a given state action pair, we take account side information obtained by exploring all the other state action pairs, where the degree of side information is high when two pairs are close to each other. This simplification provides an upper bound of the regret fundamental limit by some function of the bias band H and the minimal suboptimality gap delta mean times S-lib A-lib log of t. Here, S-lib A-lib can be interpreted as the number of balls needed to cover the region where states and actions are embedded. Hence, if the embedding region is limited, S-lib A-lib does not scale with the number of states and actions. Furthermore, when the span H and the minimal gap delta mean do not scale with S and A, the optimal regret under ellipsis structure is independent of S and A. Note that the span H is constant when the MDP has fast mixing or bounded diameter. So far, we have seen that a structure can reduce the regret significantly. So now, the remaining question is how to devise an algorithm that optimally exploits the structure and achieve this scale-free regret. So to answer this, we develop an algorithm based on the interpretation of the linear programming in the fundamental limit analysis. Recall that the feasibility of eta means a necessary condition to identify optimal policies. And an optimal solution eta star of the LP provides a direction of minimal exploration. Then based on this interpretation, we propose DEL algorithm, which stands for directed exploration learning, works as follows. At each time, it checks whether the current exploration rates are feasible or not with some positive slack gamma here, which makes the necessary condition to a sufficient condition. And if the exploration rates are feasible, DEL algorithm exploits an apparently optimal action. But if it is not feasible, then the algorithm explore suboptimal actions based on the direction of the estimated solution eta t. Then for this algorithm, we show that as the estimated solution eta t converges to the true optimal solution eta star, the proposed Dell algorithm targets to the optimal exploration and achieve the minimal regret. In fact, in order to show the convergence of estimated solution eta t, some additional tricks in the design of Dell are required, but I skip them in this talk. And in addition to the general Dell algorithm, for ellipsis structure, we can also able to devise a simplified version of Dell with the simplified feasible set F-lib instead of the intractable semi-infinite LP. Then for ellipsis structure, we show that this simple algorithm also achieve a scale-free regret, but its algorithmic complexity is reduced at a tractable level by the simplified feasible set. Finally, we numerically illustrate our theoretical results on a simple example of MDPs with some ellipsis structure. Here we compare algorithms that exploit or not exploit the ellipsis structure in terms of regret. The figure on the left-hand side show a significant regret reduction when exploiting the ellipsis structure, as expected from the analysis. And the figure on the right-hand side present the regret after sufficiently many steps, namely 50,000, and while increasing the number of states. And again, as expected, the algorithm with ellipsis structure has the regret that does not increase in the number of states. So in summary, in this work, we have studied the problem of regret minimization when we know some structure about system dynamics. For this problem, we obtain the regret fundamental limits through solution of a semi-infinite LP. And then we propose an algorithm called Dell that optimally exploits the structure based on the solution of the LP. And particularly for ellipsis structure, Dell achieves a regret independent of the number of states and actions. And finally, I want to mention that our work is related to some recent similar analysis in the case of structured bandit, and a few more previous efforts in the context of structured MDP. However, to the best of our knowledge, our work is the first to show that exploiting a structure can yield in this scale-free regret. Okay, this is it, and thanks for listening, and I hope you see at our poster after this session.
So we have some time for questions.
Hello. Yeah, thanks for the very interesting talk. Although I would slightly disagree that this is the first result showing scale-free exploration rate for large-scale reinforcement learning. In fact, my co-authors and I have been working on this line of work related to Bellman rank that shows polynomial pack bound for a large range of environments where you need to use function approximation. But I think it will be very interesting to see whether the scenarios we find to be structured and exploitable have a low complexity parameter under your definition. So that's the first comment. And that will give you more examples where your structure parameter is low beyond the Lipschitz case. The second comment is that even for the Lipschitz case, there has been work back in 2003 by Sham Kakade and John Lanford on metric E-cube, which does optimal exploitation. And later by Ron Parr from Duke University and Jason Parsis, who has the algorithm called C-Pace. Can you comment on the comparison of your guarantees to theirs? Thank you.
Thank you for the really useful comments. Actually, I skip all the details, but Essentially, we provide a problem-specific lower bound. As far as I know, some other work that claims scale-free regret or scale-free sample complexity analysis is based on some kind of minimax lower bounds, where the system seems a little bit on an artificial way. But we provide here a problem-specific regret lower bound and with some log of t regret. But as far as I know, minimax analysis may have results with some scale root of t or something else. And yeah,
We have time for one more question.
Hi. So I was wondering if you could comment on the the algorithm you introduced towards the end, the result you mentioned for its regret, does it actually? I was surprised to see no properties of the set phi that actually enter the regret bound. So if I have a very complex class phi versus a simple class phi, where does that actually show up in the regret analysis? And also, when you have to estimate the KL divergences that go into the constraint set, where does the estimation error in the KL divergences enter the regret bounds?
Okay. In our LP formulation, the feasible set F is actually the function of structure capital phi and the function of given MDP phi. And in particular, where the structure kick in is that this LP constraints compares all the confusing MDP that satisfy the structure but has different optimal actions or policies. So I hope this will answer your question.
Let's thank the speaker again. Next, we have 5 spotlight presenters, the first of which will be Jiankong Wang, and he will be speaking about acceleration through optimistic no-regret dynamics.
Hi, everyone. This is a joint work with Jacob Abernathy at Georgia Tech. So I'm going to talk about a new interpretation for some algorithms in convex optimization. And we know that there are many algorithms to solving convex optimization, like gradient descent, Nestor method, heavy ball. For smooth convex problems, the base conversion rate is 1 over t squared. T is the number of iterations. And when the problems are both strongly convex and smooth, then one can get an accelerated linear rate, which has a base dependency on the conditional number kappa. On the other hand, in online learning, when the learner has a convex loss function, the average regret is 1 over root t. And when the learner has a strongly convex loss function, the average regret is 1 over t. So it appears that there's a gap. There's a gap between the regret, the average regret in online learning, and the conversion rate in offline convex optimization. And in this work, we bridge the gap. So our work is by constructing a zero-sum game for the underlying optimization problem. So this is a zero-sum game. And there are 2 players, S players, Y player. S player try to minimize the payoff function G, and Y player try to maximize the payoff function G. So the definition of payoff function G is S comma Y minus the conjugate of F. And F is the underlying optimization problem. So the minimax of G is actually equal to min F. And approximately solving this zero-sum game is equivalent to solving the underlying optimization problem approximately. A way to solving the zero-sum game is putting 2 online learning algorithms against each other. So both learners use some online learning algorithms to determine STYT. And the goal of the online learning algorithms is to minimize the regret. And in our setting, we consider that the loss function is associated with a weight alpha t. So after the t iterations, the meta-algorithm outputs x bar t, y bar t, which is the weighted average of what the learner pressed over the t iterations. So one can show that the function value at s bar t is an epsilon approximate optimal solution to min f, the underlying optimization problem. And the epsilon is equal to the sum of the weighted average regret, which is the regret divided by the total weight, AT. So natural method is an instance of the least meta algorithm when the y player plays optimistic forward leader on its loss function and the s player plays gradient descent on its loss function sequence. And the s bar t, which is the weighted average of what the s player plays, has a recursive description which exactly matches that of the natural accelerated method. So one can also use different online learning strategies, like mirror descent or be the regularized leader. And that will lead to other accelerated methods of natural algorithms. Heavy ball is also an instance of this meta algorithm when a y player plays forward leader instead of optimistic forward leader. By using the regret analysis, we observe that surprising cancellation in the regret of both learners. And this leads to the accelerated rate 1 over t squared. And the same techniques actually go beyond 1 over t squared. We also get an accelerated linear rate when the problems are both strongly convex and smooth. And using the same framework, we also get an accelerated proximal method and accelerated framework. So come to our poster. Thank you.
Thank you. The next speaker will be Christoph Dunn. He will be speaking about on Oracle efficient PAC-RL with rich observations.
This work is on exploration with functional approximation in reinforcement learning, and it's joint work with Nan Jiang, Akshay Krishnamurthy, Alec Agarwal, John Langford, and Robert Shapiro. Exploration refers to taking actions to gather data that provides us with a comprehensive view of the environment. In what is called a tabular setting with few possible states, this is well understood, and we know many provably sample-efficient approaches. However, many common exploration heuristics, such as epsilon greedy, can be inefficient and have exponential sample complexity. While tabular is the main focus of most theoretical research, most practical problems are not tabular. They have rich observations, such as images or text. How to do provably sample-efficient exploration in these cases is a fundamental but understudied problem in reinforcement learning. My co-authors have been pursuing this direction of research and have made several advances in the past. The first one is an algorithm called LSVEE that is provably sample efficient in problems with stochastic rich observations and deterministic hidden state transitions. Its sample complexity only depends on the small number of hidden states and not at all on the number of possible observations. This was then followed up with an algorithm called OLIVE that extends this result to more general problem classes, and those classes include problems with stochastic hidden state transitions. While highly promising, these methods enumerate possible or candidate value functions, and that is impractical in most applications. Therefore, in this work, we propose a new algorithm called Valor that is not only provably sample efficient, but also provably computationally efficient in the setting of LSVEE. In the more general case of OLIVE, we provide a negative result that highlights the computational challenges there. Our algorithm Veiler works in settings that are motivated by empirical research, where, for example, we can represent the hidden state space as a simple grid world as shown on the left. But the agent only observes, for example, a rendered 3D view of the environment, which requires function approximation. And there are many possible observations for a single hidden state. We also assume that the hidden state dynamics are deterministic. That means taking the same sequence of actions yield the same hidden state. Exploration in this case then boils down to exploring all possible action sequences. And doing so efficiently requires pruning action sequences that lead to states that we have explored previously. Therefore, to do this, the existing LSVE algorithm performs a state identity test based on the observations. And this test enumerates possible or candidate Q functions, which is impractical. Therefore, in this work, we instead formulate this problem in terms of the state value function V and a policy function pi. This reparameterization allows us to write a state identity test that is a linear program in the state value functions, and that can be carried out efficiently for many function classes. Therefore, we are able to prove eventually that Veiler is not only statistically but also computationally efficient in problems with deterministic hidden state transitions. But what if we want to remove that determinism assumption? The existing Olive algorithm is the only algorithm that we know that is provably sample efficient for this general problem class that we have in mind. However, we prove in this work that even when we apply it to tabular MDPs, it requires NP-hard computation. And since most common optimization oracles, such as least squares regression, are computationally trivial in this case, that means we cannot implement Olive with such optimization oracles. However, this is an algorithm-specific result and therefore not the end of the story. There might be other algorithms that are provably sample and computation efficient in the general setting with stochastic hidden state transitions, but finding such algorithms is still an open problem. To learn more about this work, please come to our poster with number 111. Thank you.
The next speaker will be Zakaria Mahmedi, and he will be speaking about constant regret, generalized mixability, and mirror descent.
Thank you. Hello, everyone. This work is about characterizing conditions under which a constant regret is achievable in the game of prediction with expert advice. So consider a situation where you would like to predict the movement direction of the daily stock price. And to help you with this task, you have access to predictions from experts. So each expert gives you a probability P of seeing the stock price going up. And you would like to aggregate these predictions or mix them in a way to make your own predictions with the goal to perform as good as the best expert after any number of rounds. So this is an instance of the game of prediction with expert advice. And your performance is measured with respect to a loss L, which typically takes two arguments. In our case, the first argument is either 0 and 1 for the stock price going down or up. And the second argument is the probability P of seeing the stock price going up. It turns out that if the graph of this loss function is curved enough, or more precisely mixable, then there's an algorithm called the aggregating algorithm that you can use to perform as good as the best expert after any number of rounds. To formalize this setting, in the game of prediction with expert advice, at each round T, the learner observes the predictions of the experts, and then he picks his own prediction, and then the outcome of the environment is revealed. And then the learner and the expert K suffer loss depending on their predictions and the outcome of the environment. So when the cumulative loss of the learner minus the cumulative loss of expert K is bounded by some constant R that does not depend on the number of rounds T, then we say that a constant regret is achievable. And this work looks at conditions under which this constant regret can be achieved. An example of this condition is mixability. So when a loss is mixable, then you can use the aggregating algorithm, which essentially runs exponential weights over experts to allow you to achieve a constant regret. So mixability is a geometric property of the loss. In fact, a loss is eta mixable if and only if the exponentiated superprediction set is convex. The superprediction set is the region in the northeast of the loss curve. And if you take this region through the exponential map and the resulting set is convex, then you say that your loss is eta mixable. And then you can use the aggregating algorithm to achieve a constant regret. In 2015, a generalization of this mixability condition was introduced called eta phi mixability, which, when it's satisfied, you can use this generalized aggregating algorithm to achieve a constant regret as well. This generalized aggregating algorithm, now instead of running exponential weights, it runs a mirror descent step instead. And the generalized mixability condition is satisfied if, for all weights over experts, for all predictions of experts, there is a prediction that you can pick such that for all outcomes of the environment, your loss is less than this mirror descent step on the right-hand side of the inequality. But a nice characterization of this condition was not given, so it was unclear where losses can be called eta phi mixable. So our first result was to give a full characterization of this eta phi mixability condition. So loss is eta phi mixable if and only if a convexity condition involving the entropy phi is satisfied with respect to the Shannon entropy. And then using this characterization, we showed that the Shannon entropy is fundamental in two different ways. The first way, if a loss is eta phi mixable, it must necessarily be eta phi Shannon entropy mixable. And the second result that shows the fundamental nature of the Shannon entropy is that the generalized aggregating algorithm achieves the lowest worst case regrets when using the Shannon entropy. And then the final result that we show is we take advantage of the similarity between the generalized aggregating algorithm and the mirror descent to devise a new adaptive version of the aggregating algorithm. And we demonstrate that in some cases we can even achieve a negative regret. In that case, the learner performs better than the best expert after a number of round T. And with that, I conclude my talk. Please come to the poster. Thank you.
Go ahead. Thank you. The next paper will be presented by Chen-Yu Wei, and he will be speaking about efficient online portfolio with logarithmic regret.
Hi, I'm Chen-Yu Wei from USC, and this is a joint work with Haipeng Luo and Kai Zhen. We considered a decade-old problem called online portfolio management, which is a multi-period investment problem. And let me first introduce our problem in a single trading period. Assume that our money is wealthy in the beginning of the trading period. We will decide the distribution of our money onto a set of stocks. For example, here we put 50% onto the first stock, 30% onto the second, and 20% to the third. Then in this period, the price of each stock may vary, and we have some gain or loss. Our final wealth is the sum of the final amount of our money on every stocks. If we call the distribution that we made as the vector xt, and we call the relative growth rate as rt, then we can see that our final wealth is our initial wealth times the inner product of xt and rt. We don't make any assumption on the magnitude of rt. So if this procedure repeats for capital T times, then our final wealth divided by our initial wealth is the product of xt and rt among all trading periods. We call this ratio the gain of the player. To judge whether the player is doing a good job or not, we compare the gain of the player with the gain of a benchmark strategy. This strategy is the one that always uses the best but fixed distribution over stocks. Minimizing the ratio between the benchmark gain and our gain can be written as an online convex optimization problem with some loss LT. And our goal is to minimize the regret. But there is some caveat when solving this problem using standard online convex optimization algorithms. This is because the gradient of the loss can be possibly unbounded. More precisely, the gradient can scale with a maximum ratio between the growth rate of two stocks. Since we don't make any assumption on the relative ratio, it can be potentially unbounded. So let me review some previous results on this problem. First, this problem has a regret lower bound of n log t, where n is the total number of the stocks and t is the total number of rounds. The algorithm universal portfolio achieves this lower bound, but it requires some sampling procedure that requires very large number of samples. There are other efficient algorithms like online Newton step and soft base, but their regret either have a dependency on G, which is the largest ratio between two stocks, or square root T dependency, which is much larger than the lower bounds log T. So a long-term question is that whether we can get nearly optimal regret with efficient computation. Our work makes a significant step in answering this question. We get the first practical algorithm whose regret is logarithmic in T and without any dependency on G. And the computation only has small polynomial in N and T. Our algorithm, Barron's, is a modified version of online Newton step. We observe that large regret often happens in the following case. This case is when there is a constantly bad stock suddenly becoming very good. When it becomes good, the original online Newton step cannot track the change quick enough. Our algorithm is different from online Newton step in 3 aspects. First, we add an additional regularizer so that the player will not use too extreme distributions over the stocks. Second, we use coordinate-wise learning rate and increase the learning rate in the directions that corresponds to worse stocks. These lead to a fast recovery when the bad stock suddenly becomes good. Third, when some condition holds, we will adjust the parameter and restart the whole algorithm. This has the effect of adapting to the maximum relative ratio. We believe many of the tricks we use here may have potential use in other problems. If you're interested about them, we'll come to our poster. Our poster number is 157. Thank you for listening.
The final speaker of this spotlight session will be Christian Kröhr, and he will be speaking about solving large sequential games with the excessive gap technique.
Hi, everybody. My name is Christian. This is Join to Work with Gabriele Farina and Thomas Sandholm at CMU. So I'm going to be talking about solving sequential games, and these are games played on a tree such as this. Every node in the tree, sorry, I hope everyone can hear most of what I said. So it's going to be a game played on a tree, and every node belongs to some player, and the set of actions are just the set of branches at that node. And so we're going to be interested in zero-sum games where we have just 2 players, player 1 and player 2. Player 1 wants to minimize the expected value over the leaf nodes, whereas player 2 wants to maximize the expected value over the leaf nodes. We also have chance nodes, which give a fixed distribution over actions always. And then we have information sets, which are groups of nodes that players can't distinguish among. And these can be used to model things like, for example, in poker, which hand your opponent has. Okay? Now, the problem that we're interested in is computing a Nash equilibrium for these games. And so let me just very briefly mention one application. So Nash equilibrium for extensive form games was recently used in several breakthroughs for making superhuman AIs for poker games. Okay? Now, all of these breakthroughs were based on a particular algorithm called the CFR algorithm for computing Nash equilibria. But let me just briefly talk a little bit about what kinds of algorithms you generally can use for this problem. So first off, you could use linear programming, but it turns out that the simplex algorithm as well as interior point methods are too slow in practice. And that's because each iteration is just too expensive to compute. In practice, the most popular thing has been these CFR algorithms, which in theory converge at a rate of 1 over square root t, where t is the number of iterations. But in practice, they tend to converge at a rate of 1 over t, or sometimes even better for the sort of best variants. On the other hand, another type of method you could use are first-order methods, or gradient descent-like algorithms, if you will. If you set them up right, these algorithms actually converge at a rate of 1 over t, in theory. However, in practice, they also converge at a rate of 1 over t, and so it's been the case that, especially for large-scale games, CFR variants have kind of performed better in spite of this sort of worse theoretical rate. And so in this work, we try to sort of ameliorate this and try to sort of bridge this gap a little bit. And what we do is we introduce a particular variant of a first-order method, which is a tweaked version of the excessive gap technique, which was introduced by Nesterov. I won't go over all the details of how we changed the algorithm, but basically it uses a particular aggressive step sizing scheme to try to speed up the practical convergence rate. And now I'll just briefly go over some particular experiments we did on running this on large-scale games. So the experiments are as follows. They're real-time sub-games from the Brains versus AI competition. So this was the competition where the Libratus AI played against 4 top poker pros. And in real time, it would solve sort of sub-games that it encountered. And so these have to be solved very quickly because the humans are actually waiting for the AI to respond. I'll show you experiments from a single game that has about 54 million leaves in the game tree. And I'll show results for 5 algorithms. I'll show the EGT algorithm without our tweaks, and then I'll show our aggressive variant, and then I'll show 3 CFR variants. Okay? And so here I'm showing the convergence rate as a function of the number of gradient computations, which is sort of the most expensive operation involved in this. And the takeaway point is that our algorithm is the green line, which you see sort of in the middle there. And so we managed to beat 2 out of 3 CFR variants, although we're not quite as fast as CFR Plus, which is the fastest of the algorithms in practice. So we sort of bridge the gap a little bit and give the first results showing that it is possible to beat the CFR algorithm in practice as well as in theory, although we haven't quite reached the best variant of it. And so in conclusion, we introduce an aggressive variant of the EGT algorithm. We give the first comparison of first-order methods and CFR on real large-scale games. And we show that first-order methods can indeed be made faster than all but the best practical variant of CFR. And sort of for the future, I think this also suggests that there might be other first-order methods that could in fact be competitive even with CFR+. So you can find the paper on my website, which is shown here, and please come to the poster, which is number 77. Thank you.
This concludes our session. Thank you very much for your attention. If you would like to follow up with any of the authors, you can find them at the upcoming poster session. Let's give them a final round of applause.